I'm Juliet Mason, and we have my partner.
And I'm Jay Reckworth.
This is an image representation of our project, the galvanometers. We have two magnets right here, and then it's connected to a battery. So here's a larger representation. This right here, the blue circle, is our cylinder going into the page. You have a few wraps of copper going around, and we have it connected to our power source, the battery. It will rotate this whole thing this way. This is the general equation, the Biot-Savart loop for our solenoid. This one is for a single loop. For our solenoid, here's a basic representation. We have our theta 1 and our theta 2 angle here. And because what our demo essentially is we have about 50 loops of the copper right here at this point P at the end here. And then it all reduces down to this equation here when we have it all at the end of the solenoid.
This is our device that we put together. Actually, this is an ammeter, and we'll discuss that in a second. But this is our cylinder here, and our coils wrapped in this direction, and our current will be coming in like this. Here are two large niobium magnets that are 4 centimeters by 4 centimeters by 2 centimeters, giving off about 0.4 Teslas. And then this is our device that we use to bring our needle back to baseline. So when this rotates, the weight on those two hex nuts will pull it back. Using the left-hand rule, you'll understand why the torque on this cylinder rotates clockwise. So this is north, south. So you've got, using the left-hand rule, you've got your magnetic field going this direction. You've got your current going into the cylinder. So your force is down on this side. That's why you've got a torque in this direction. We've run several tests already, and you can see that we've actually calibrated our device from 0 amps all the way up to 0.6 amps. And one of the things you should note is that it's not linear. All right, so that this is 0, this is 0.2 amps, 0.27 amps, 3 amps, 0.45 amps, and then 6 amps.
0.6 amps. The first one that we're testing, this is going to be our first measurement here, 0.2 amps, and this is based on two 100 ohm resistors and a 9 volt battery. So this one will only move just a little bit. The second one we have, this will be 0.27 amps, and we have three 100 ohm resistors connected in parallel and a 9 volt battery. Right here on the breadboard, you can see that. So this one's moving a little bit more. So right now we are using two 1.5 volt batteries connected. So that's a total of 3 volts. And we have this connected to a 110 ohm resistor. And this one is like that. The next one that we are doing is 0.45 amps over here. We have a 1.5 volt battery that's powering three 10 ohm resistors. The last one that we are doing, this is the 0.6 amps all the way over here. We have two 10 ohm resistors connected in series using a 3 volt battery for power. And this one really moves.
Running the FEMM program and putting the 0 point right in the center of our coil, it shows that the torque is clockwise and has a value of 4.61 to 10 to the minus 4th Newton meters. And this is compared to the torque calculated by our counterweights, which is 6.86 times 10 to the minus 4 Newton meters.